This information is brought to you by Charles Sturt University.
Welcome, guys. So what we're talking about yesterday is looking at probability distribution. So I just want to finish an extended example on that. So we looked at this one yesterday. And we were considering what's called a bivariate distribution, which is just pretty much two variables just seeing how they're linked together. So two variables just seeing an interaction. So x was going across, so x had values 1, 2 or 3 with certain probabilities, and y was -1, 0, 1 with some probabilities. So we have the margins, so the numbers on the bottom here, for example, would be the probability distribution of x by itself, and these numbers would be the probability distribution of y by itself, and the table in between just tells you the interaction between the two, essentially. And so I briefly mentioned looking at joint probabilities, which are numbers in the table, marginal probabilities, which are the ones on the outside, the margins, and the last one is conditional probabilities, the ratios of those, essentially. So, but you can do other things with it. So I got some various questions. So are x and y independent? So essentially, if they're not independent, what would they be? What's the opposite of independent? Dependent, yep. So pretty much, are these variables independent or dependent? So what does that mean? Does the outcome of one variable have an impact upon the other or not?
No. It doesn't.
There's two people next to it, they disagree.
It limits what it can be. Like it puts it in it. If you choose an x value, then you're limited with. No.
So.
No.
So if you choose a y value, if you choose x equals 2, does it have the same? Is the probability for y the same as it would be for x equals 3, or x equals 1? So if the value of x you pick changes the probabilities of y's, then yes, there's a dependency. If the probability is the same every single time, then they're independent. That's sort of one way of understanding it. The easiest way to check is the main rule. So if you remember, probability of A and B equals the product of these two if they're independent. Precisely when they're independent. So that's sort of a mathematical definition of independence. So we can check that out. So let's just check what's the probability that, say, x equals 1 and y equals -1. Let's check that joint probability out. And we're just picking the very top square. That's all I'm really doing here. What's the joint probability of x equals 1 and x equals -1?
0.
0, that's right. So it's just that number there. That's a 0. On the other hand, let's work out the probability of x equals 1 and multiply that by the probability that y equals 1. So the probability x equals 1 is what?
3.
Yep, so that's that number down the bottom. And then what probability that y equals -1 is equal to 0.3. And so then the marginal probabilities, as we're recapping from yesterday. And if you make the product of those two, you get 0.09, not 0, essentially. So as soon as you can see... so in this case, they aren't the same number, and so therefore that tells you they are
Independent.
Dependent. What? Dependent. So if they were equal for all 9 possibilities, that would tell you they're independent. The fact there's a difference for at least one of them tells you there's a dependency. So for example, one dependency you can see from that straight away is if x equals 1, y can't be -1 anymore. That's a strong dependency. Other than that, I mean, there's probably other ones you can work out, but that's one of the relationships between the two variables. So if you just picked a random two random variables and just put some numbers in the middle of the table, most likely they're going to be a dependency there if you pick them randomly, unless you pick them on this very precise pattern that the joint probability is always a product of the two corresponding marginal. So you can see the row total and the column total, if they take the product of those two, that should give you the individual value for things being independent. So independent has a very special pattern to it, and when things are independent, it's much easier to deal with them, etc. But not everything's independent, and sometimes that's useful too.
Maths is super easy.
Okay, let's go a few more. So question 2 down the bottom there. Just a simple one. What's the probability that y is 0 given x equals 1?
Yeah, that's really off-putting. Drinking crap like air.
So in terms of the way to do it intuitively, as I said yesterday, is to go, well, that vertical line, that line means given. So given x equals 1, so given we're in that column there, what's the probability we get y equals 0? Well, in that column, how often of the time do we get y equals 0?
0.2.
0.2, so that number there.
Yep.
And out of, how much of the time are we in that column?
0.3.
0.3. And therefore that would be the conditional probability that y equals 0 given x equals 1. So you write as 2/3, whatever that's equal to. 67% approximately. And you're going to get different conditional probabilities from that as well. So what I want to do then is to work out various expected values given these sort of things. And that's, therefore, to work these things out, you need to know what the probabilities are. So question 3, I'll read it as calculate the value we expect for y given x equals 2. Now expected value is really just a synonym for average. So what's the average value we get for y if we know that x equals 2? So the basic way of working out any expected value is to sum over all the possible values we want to consider. So sum over all the different possible y values, which would be -1, 0 and 1, they're the three options, of the value we have in mind, so y in this case, times by the probability of it happening. So in this case it would be the probability that our random variable is equal to this little variable, -1, 0, 1, just the three different things, given x equals 2. So expected value is always the value times by the given corresponding by multiplied by a probability. So in this case, it's y equals -1 to begin with. So it's -1 times by the probability that y equals -1 given x equals 2. That's the first case. The next option is when little y is 0. So 0 times by the probability. Yeah, and that's going to be 0. Plus the next y value is 1 times by the probability y equals 1 given x equals 2. That's what that sum sign means. So just summing over all the three different values we have for y in this case. Get the value in question, -1, 0, 1, multiplied by the corresponding probability. That's what always expected values are. The value times by a probability, just adding them up, adding up all these different terms.
So I assume that all just cancels each other out because you've got the -1, the +1, and you've got the 0. That would be easy.
So let's have a look what they are going to be. So we're going x equals 2. So we're in this column. So given x equals 2 in that column. So when y is -1, the probability is 0.2. So it's -1 times by 0.2 plus 0 times by, who cares almost?
0.
It happens to be
Just put whatever.
0.1 plus 1 times by,
In the grand scheme of things. That's for CV.
so basically by 0.1. So the probability that y equals 1 given x equals 2 would be that number. Now, is that right? Not quite. What have I done wrong? I didn't mean to make a mistake, but I did, so I'm trying to fix it up.
Shouldn't it all be over like 0.4?
That's right. So each of these numbers, being conditional probabilities, should all be over 0.4. That's the proportion of being in that row. So thanks. Everyone okay with that? I'm not sure if you are somehow.
Sure.
So given the calculations, and then we'll just talk a bit more about the next one,
Or heat for the probability.
what's that going to be all equal to? So you got -1 times 0.2 and 0.4, that's going to be -1/2,
I think it would be
plus 0 plus 1 times 0.1 and 0.4, so plus 1/4. So the whole thing gives you -1/4. So if x equals 2, the value we expect, the average value we would get for y would be -0.25. And it makes sense. The values for y is -1, 0 and 1. So it's got to be in that range of values. So average has got to be somewhere in the middle, roughly speaking. And given these things, the probability is more closer to -1 than anything else. That's the more common value. So the average being negative, again, matches the values essentially. So it's just a way of working out the average. Let me do that. So this one here, we've got the same table. We want to work out not a conditional expectation value, or not a conditional expectation, but just a normal one. So what value do we expect? What's the average value for x, essentially?
0.4? 0.4?
It's going to be, so it's an average. So the x value is a 1, 2, 3. So it's got to be an average of numbers 1, 2, 3. So it's somewhere between 1 and 3. Some sort of middle value. So 0.4 is not right because it's outside. The way to work out any expected value is to sum up over all the values we're concerned about. So 1, 2 and 3. Multiply the value by the probability of getting that value. So the probability of x is equal to little x. So it's always the value multiplied by the probability. So it's going to be, what's the first value we have for x?
1.
1 times by the probability that we get 1,
Which is 0.3.
which is, that's right.
I guess on 0.4 as well. It's a conditional one, right?
No.
No? Okay.
So conditional means you have to have that vertical line,
Okay.
and we have no condition here. So where'd you get the 0.3 from?
Because it's at the bottom.
Yeah. So the probabilities for x equals different values are just those marginal ones. You just read them off straight. So this is actually easier than the previous question. The next sum would be, the next x value is 2 times by the probability x equals 2, which is 2 times by 0.4. And the last term would be, so 3 times by the probability of getting 3, which is 3 times by 0.3. and then it's just a matter of basically doing the products and adding them up. So it's 0.3 plus 0.8 plus 0.9 gives you an average value of 2.
Makes sense.
Why does it make sense?
Because if you add them all up and divide it by 3, you get 2.
Okay. So this is, so if you look at the probabilities there, they're nice and symmetric, and therefore they're going to be not biased towards either eye, so it's going to be right bang. It is actually going to be a true middle value. And the middle value is definitely the 2. So these are not, so what we're doing here is we're not taking a direct average of 1, 2, 3. So a direct average would be add up numbers 1, 2 and 3, get 6, divide by 3 gives you 2. That's a normal average. This is called a weighted average. So we're weighting it by the different probabilities, so it's called a weighted average. Now, the average in the case it happens to be the same value, but it need not be like it was for the previous case. So this one was also a weighted average, and if you just took a straight average of the y's, you get 0. But this particular weighted average gives you an answer of minus a quarter instead. So it shows you it's slightly biased towards the negative values. So the last of these yeah. So again, at the same table, we want to work out what the expected value for x plus y is. Now, there are 2 ways of doing this. I'll do the long way first, and I'll show you what the short way is. But I wanted to.
Like being maths teacher. Do the hard way first and then show you the easy short. It's like the classic math teacher when it's like to find the gradient you can do all this stuff or you can just differentiate.
That's right. It's good to understand where things come from. So, the basic way of working out expected values, the way I've been explaining it, would be to sum over all the different values we can get. So we basically get an x and a y value. So we want to sum over all the different x's and sum over all the different y's, multiplied by the probability of getting them. The x is the something value, and y equals y. So that's sort of the basic approach we're going to do. That's the basic approach. Sum over all different values, multiplied by the probability of getting it. So I'll just write down this sort of sum. So there's options. Basically, let's consider x equals 1. And what's the first y value you might consider?
-1.
-1. What's the probability of getting both x equals 1 and x equals -1 at the same time?
That's 0.
0. It's just that number there. Right, it can't happen, that's correct, just someone said that. What's the next possible arrangements of x and y we want to get? Well, let's just go along, just go across the table. The next one would be x equals 2 and y equals -1 would be the next sort of value, and its probability would be 0.2. Next one would be x equals 3 and y equals -1, and multiply that by the corresponding probability of 0.1, etc. So you keep going at each different value.
Oh, that's going to take forever.
So it would be x equals 1 plus y equals 0 times by its probability. So what's the last term? Just to say the pattern is.
X is 3, y is 1.
So x equals 3, y equals 1 times by the probability of getting both at the same time, which will be that last number, 0.2.
It would literally take you like your entire life. Those 2 things.
You probably could do it all without a calculator in 5 minutes. So So not, you do it without a calculator. So no, it will not take all your life.
If you add another row, it just keeps getting bigger and bigger. Just add another row.
Yeah. So if you add more rows, it gets
You're stuck there for another 4 years.
So you're going.
Add rows, David.
Why did I do that one first? Is because I'm trying to sell you. Maybe it'd be nice to find an easier way of trying to do it. And so.
Get like EX plus EY each to their own.
So the answer is. The expectation is a linear operator, which is a very fancy way of saying you can just take the sums outside of it. So anytime you've got the average of the sum of two variables, you can just do each of them separately, add them up later. Another example of a linear operator you've seen is differentiation. That's linear too. So if you want to do differentiation of a sum, you just do differentiate each part separately. Same idea. So you can just do them separately. And so we worked out the average value of x already, that was 2, so we got that one. How would you work out the average value of y?
Is it minus 0?
Same sort of thing. Why don't you do it on your piece of paper in front of you now? Yeah, I'm serious. So you work at the table, see if you can work out what the average value for y is. And then from adding the sum. So if you don't want to do that, you can just fill in like gaps in the long way of doing it. My suggestion is easier to work the average value directly.
This is 0.1.
Anyone want to tell me what I reckon the answer is?
0.1.
I'm going to lock in 0.1 as well.
Because that's just the answer. It's important to know how to get it more than anything else, of course.
2 minus 1 times 0.2 plus 0.0 times 0.3 plus 1 times 0.4. Is that how you do it? What a feat. Character creation,
As you're saying, it's basically going through all the different y values, so -1, 0, and 1, going through all the probabilities that go match it up with it. Just take the product of each of them and add them up. So it's the -1 times by 0.3 plus 0 times by 0.3. Just going down the values, plus 1 times by the 0.4. Just going through all the values, matching probabilities, take products and add them all up, all the values. Because there's a 0 in the middle, there's a little 2 terms there, and you get the 0.1. Just using a calculator if you need to. So you're okay with that? So, back to our problem down the bottom here. The average value of x was 2, the average value of y was 0.1. So the average value of the sum of them would be 2.1. So if you had to work out, so the expected value of any sums can be done this simple way. If you had to work at other things, so you had to work at the expected value of x times by y, which I'm not going to do, you have to do it really this long approach at the top here. There's no trick for that. You can't just do, oh, that's ex times ey. It doesn't work like that. It's not true. So the expectation, or averages, preserve sums, because if you think about it, averages are just adding up a bunch of numbers. So adding one part separately and the other part separately works. But you can't do products. So the expectation of the product of the two really has to be done separately. You know, why would you ever do that? So this value here, so exy minus exey, is called the covariance between x and y. It's a measure of the related variability between the two of them. So there are reasons to do those sort of things. We want for, as you can see, it's for this sort of stuff, a lot of small calculations to do that. I mean, you could do it with a little time, but there's lots of things that are useful for us. So it tells you how these two variables are related to each other. So last of these examples is the one we looked at the other day, and this was the headcount data for Orange and Bathurst campuses. So looking at the gender ratios, essentially, of students from 2014. That's the actual raw counts from 2014. We can make that into a probability distribution simply by dividing by the grand total. So if you divide by 3572, that would be, to two decimal places at least, the probability distribution for it. So that's called a frequentist approach. Really, we're just using the frequency of what we've seen to approximate a probability distribution, essentially. Now, that was only 1 year of data, only 2014. And so, really, it's best thought of as being just a snapshot. The proportions are not the same in 2016. Because some people have left the university, and for example, you guys have come since then. And so that's changed the proportion slightly, I'd imagine. There's a lag in the data. So since 2016 should include all sessions worth, and since the state was only about a week ago, there's no way I could get access to that data yet. It takes a while to get access to it. Even 2015 is hard to get for some reason. But anyway, so you might want to ask various questions with this sort of data. You might want to ask, well, what proportion of the Bathurst campus are female, etc., which is a conditional probability, which we did do this already. But the other question is, well, are the two variables independent? Which is another way of saying, is the gender ratio and the Bathurst campus and the gender ratio and the Orange campus, are they the same or not? If they were the same, that would suggest they're independent. If they're different, it would be a dependency. And the dependency, if there is a dependency there, it's not based on the town, I'm sure. It's based on the courses that get done at the various campuses. So Bathurst is a much bigger campus than Orange is. Orange is mostly focused on health, which attracts certain people.
Have you seen the amount of paramedics here though? Like, oh my god. I swear to god, like 90% of everyone here is paramedic. What did you show?
They probably stand out because they have a uniform.
The rest of them are nurses. Yeah.
You guys make up some of the campus though, and you guys aren't nurses or paramedics.
Oh yeah. Once they convert it, it's really cold.
So, how do you work out if they're independent? So what's that? Check them independence again.
Well, they are. It doesn't matter if they're like times some stuff.
So if you basically, if they were really independent, then the the top entry, so the number of male Bathurst people, probably even being male in Bathurst, would be the marginal probability of 0.41 times by the 0.83. That should give you the other value, the key definition of independence. Let's get some Excel to help us out here.
Excel.
So here's all the answers essentially. So that's the raw counts. You can work out the proportions. That's after a few more decimal places than what I've put on the screen. If they're independent, so essentially, let's work it out from scratch. So if they really were independent, then the probability of being male and Bathurst would be the product of that 41% there, probability of being male, times by the probability of being in Bathurst. So if they really were independent, that would be the value we'd expect to get. Because if they're independent, it's just a probability of the individual things. And you do the same for other ones. So probability in orange would be the probability of being male times by the probability of being orange. Probability of being female in Bathurst would be the probability of being female times by the probability of being in Bathurst. So the probability of female in orange would be probability of orange times by the probability of being in orange. So that's what they would be if they were all truly independent. How do those numbers match up to what we actually have? So we're comparing these ones here.
Close enough.
Yeah. So are they the same or not?
Pretty much.
Now they're not identical, but the fact that they're a sample, right? So they're just a snapshot for one particular year. Is they may change from year to year. So the fact that they're not exactly independent is not a big deal. But are they close enough to independence to suggest that that would be a pattern from year to year?
I'm going to say yes.
So where's the biggest difference? The biggest difference is that one there, the orange males, is where the biggest difference is perhaps. Which would be to the nearest percentage, it's still 7%. So it's to two decimal places, and it's not changing anything. So in order to actually test things out for sure, it's the realm of stats. This is my little plug that you can learn more mathematics than this. So using the methods of stats, using things like chi-square tests, you can actually test these things out to test if it really is close enough or not. So there are lots of other uses for maths, and which kind of there is.
Really?
Yep.
Wow.
And so I just try to plug it, but
That's going to do so many things.
you can
At least three.
So there is a little, very small difference here. The question you ask yourself is, okay, so maybe even if there is a dependency, does it make any difference in the world? Does it have any relevance to when we're comparing the campuses? And the answer is
Not really.
probably not. And you can see that from the numbers. What you can also do is work out expected counts. So these are the average values, and how we get these is using the binomial distribution now. So the expected value for binomial is n times by p essentially. So these are the expected counts, and you can, if I hide some columns, rows even, you can compare them to the values we observed and the values we expect. Now you can see there's a little difference here. So 22 people over almost 1,200 though. So if these are the values you would expect to get if they really were independent, this is the values what we did get. So in orange you can see there's a difference of 25 people, 24 people. which over 366, it's as much as Moss Campus, it starts to be a very small, but still a natural effect. And the difference is probably you probably had more nursing here in Bathurst Campus.
Yeah, obviously.
So it's
there's only 2 courses here. Paramedics and nursing, they're like the same thing. So one's like a
You forgot about teaching.
teaching. Oh yeah.
so. Hopefully, you guys can change the gender bias in your course, and we also encourage people to change the gender bias in nursing too, for that matter.
Gender bias.
Well done to you. You're doing your bit. Okay. So basically, what we've done in this topic is looked at all sorts of ways of counting. So we started a while back counting different bases, so looking at hexadecimal and binary in particular. Then we looked at ways of counting the number of options things arise, which is combinatorics is a fancy way of doing that. In particular, we looked at combinations and permutations and factorials as special cases of those sort of things. And then we sort of finished looking at probability and probability distributions. Essentially, is what we've done in this sort of section of the subject. It's going to be assessed in the online assignment. Who's had a look at that? Who's done it all? No one? That's fine. But it's good to have a look. And how it works, just reminding you, is that you can go in and view at any point in time. You can type a few answers in. As soon as you type it in, it saves it automatically. If you're not quite sure, you can press the word save. It just saves your answer. But then you can exit and come back later. Once you hit the submit button, that's it. You can't access it again. If you press submit by accident, you can ask me to undo it.
Oh yes.
But that might be difficult. I mean, I can see your answers. So please.
So if it's like way off, she'll be like, yeah, he's probably just stupid.
It doesn't. I mean, it doesn't help you very much, really, just submitting early because you don't get any. There's no feedback until 2 or 3 days after the due date. So even if you submit it, it doesn't tell you what you got right or wrong. It just says you've submitted it. So what will happen is, the Monday after it's due, if you go back in at that point in time, you'll be able to see what the answers are and what you got right and what you got wrong, and it'll give you a bit of feedback. It's just how you work out what the answer is. So solutions essentially. And why I didn't do it immediately afterwards, just if people want to submit it late. If you want to submit it late, you have to take a 10% late penalty. But 10% late penalty is much better than a 100% late penalty, essentially. So I'd encourage you to get it on time, so you don't have any late penalties. But I've given about 2 days grace. So for assignments, I give maybe takes a bit longer to mark them. So I give 10 days grace. Having said that, the mark goes down 10% each day. So
so you get it in within 9 days.
If you get within 9, if you get the whole thing right and submit it in 9 days, you'll basically maximum mark would be 1 out of 10, effectively.
Yes.
That's still a mark.
Yeah.
So that's still a mark.
Better than 0.
But so normally it's just best not. It's normally in your interest just to submit it on time. You normally maximise your mark that way. Most people. So that's how it works. There's no. I really want to stress. There's no time limit. There is a due date though. So once the due date comes around, you can't change your answers anymore. So as I said, I will accept. So I do accept late submission. So you can, even if it's late, you can change your answers and then hit submit at that point in time. But if that's the case, then I'll give you a late penalty. If you happen to type all your answers in today, for example, and then forget to submit it, hit the submit button till the day afterwards, I can seamlessly type the answers in, and I won't give you a late penalty that one. So, well, if I can see if it's gibberish or not.
Oh man, with the submit of this.
So, in order to get you ready for the assignment, make sure you do some practice. So that's what we'll be doing in tutorials, and we'll just finish that today as well, or online meeting for the distance students. And do some exercise from the study guide. So the sort of formulas that we covered, just as a recap, we looked at that base arithmetic. So we looked at converting any different bases to decimals. There's different ways of writing down. That's the.
I was like, that's crazy. How many brackets is that? It's like 6 on one side.
That's the most efficient way of doing it. It's just how to write it down, that's all. And then, so we did different ways of converting to and from different bases to decimal. We looked at adding in different bases, which is pretty much using the algorithms you did back in primary school for adding in column addition, column subtraction, long division, column multiplication, that sort of stuff, but just applying it to different bases. We looked at counting, so the multiplication rule, if you're doing one choice and another, it becomes multiplication. If you're doing one choice or another, it's addition. But they really, and those are special cases of independence and disjoint, which we know what the words mean now. We looked at ordering elements, and if you're ordering all of them, it's a factorial. If you're ordering some of them, it's a notation. If you're just choosing elements, it's a combination. That's C letter. And we did some rules for probability. So the one that's the hardest to remember, I think, is the one in the middle here, which is that conditional probability, because that's the one you've seen least in your times of school, etc. as well. And that's what we did yesterday was the expected value, or the mean, the top row. The second one is the variance. And how do you get the standard deviation from that?
Square root that.
Just take the square root of it.
So good.
And the last one is the Z scores, or standard scores. That's what we did yesterday.
Alright.
And then there are two special distributions we had, was the binomial and the Poisson.
Just hated it.
And I've just put the simpler version of the formula up there. And it's sort of a summary of the formula. So those formulas, you need to write down as many of those on your cheat sheet for the exam as you need, essentially.
It's like just rather than like a weird scroll, like a crazy maniac.
Well, you have to read it. So if that's how you'd like to work. So what we'll do is we're going to have a lecture-free period for the next 2 weeks. It's not a holiday. So the assignment's due in that time period, so I expect you'll be doing some work, for example. It's also got an opportunity to catch up on anything you've been missing, etc. So you guys have been turning up to lectures, have probably not so much to catch up on. Other people might have more to catch up on. But yes, that's sort of an opportunity. And even if you're up to date with this subject, you might want to catch up on others. Up to you. So what we'll do after the break is we'll start looking at graph theory. Looking at what a graph, and what I mean by graphs is I don't mean XY plots. I mean networks.
No.
It's a bunch of nodes and edges and things like that.
But I like XY plots, they're easy.
Oh, graph theory is pretty easy too.
Oh, okay, that's right.
The difficulty of graph theory, there's lots of definitions to learn to begin with. That does get in the way to begin with.
When you say graph theory is easy, was this easy? Was this stuff easy in your standards? Like, what is the standard?
The hardest.
What's fast is easy.
Yeah, what's hard? What's easy? Yeah.
So what's hard and easy depends on you, really. At the end of the day, doesn't it?
No, you're the one teaching it. You're the one teaching it. Like, would you consider this probability stuff hard?
So the difficulty with probability is not the formulas, as in the hardest formulas are those ones in the slide that probably.
There's no numbers in them.
So that's the hardest formulas. The difficulty is you can ask very hard questions with probability and counting, if you can see, because there's lots of special cases to consider.
Just combine all the things into one.
So that can be the harder part, and so certainly some of the common orits, the counting part, can be quite difficult. Like as we saw when looking at number of poker hands, for example, and that was thinking through all the possible outcomes is actually, and getting everything right is tricky. Basic probability, which is take a ratio, how many things are out, over the total number, that concept most people understand. So that it's easy in itself. Just as long as you're not counting too complicated stuff, it's okay. So the range of difficulty can go from simple to quite complicated.
Very.
So that is a political answer, probably.
That's a very different answer, but anyway.
So the hardest part most people will find, I suspect, is more the abstract sort of stuff. So graphs are, it's a picture on a page. You can see what it is. Not what it is. So being more concrete, more likely. But I don't know. You can tell me later if you think you like it or not.
Can't wait.
But anyway, so that's what we'll do after the break. I'll see you guys in the tutorial later today.
Computer editor.
You are currently the only participant in the conference.